important aspect in design of control, and we are already in the control part. So we will study the transient response specifications. You remember when we have studied the logarithmic decrement, we mentioned to you that we can define some parameters for the system. And we have seen how we can determine using just the logarithmic decrement for the underdamped system, how we could define the stiffness, the mass, and the damping ratio, and so on. Today we will see the same thing, but for control part. So to see the control part, how the system performs, we need to know some specifications for the system, the response of the system. These specifications, I will cite them here: the delay time, the rise time, the peak time, the maximum percent overshoot, and the settling time. We will go in the next slide to explain in details what each term of these means. لأنه some elements or some systems, whether it is mechanical, electrical, when they have energy, they build energy, they respond to the step response. If you give them a step input, they will have an overshoot because of the energy stored in this system. They will behave like this. So before they go to the steady state, we need to know this transient behavior. This is called, that's why we call transient response specifications. So from here to here, the transient behavior is for a short period of time. So this is a response, transient response. And we need to know these transient characteristics that are the maximum percent overshoot, how much it overshoot, the delay time, the response to reach 50% of its final value. We need to know the rise time. We need to know the time, the peak time for the first peak, what will be the time for the first peak, and what will be the time, the settling time, that the time or the response will start settling and go to the steady state. So these are known as the transient response specifications. We need to know these ones if we later on we would like to control the system and to make it faster or to make less overshoot or to make faster, yani less settling time and so on. So these are needed for the control parameter. These are the transient response, and these are needed parameters for the control. So this is the introduction. This is, I already mentioned this one. Because systems that stores energy cannot respond instantaneously, they exhibit a transient response when they are subject to inputs or disturbance. So consequently, the transient response characteristic constitutes one of the most important factors in system design. So this one we already mentioned. Hmm. This one also we mentioned it. So these are the specifications that we would like to define now. This overshoot from here to here, how the system goes. This is called the maximum percent overshoot. This is known as the delay time. This is known as the rise time and the peak time and the settling time. These are called the transient response specifications. So we will go in details to this one. You remember, Shabab, when we defined in chapter 8 the uh, the response for the first order, for the second order system that is subject to a unit step input. If you have a unit step input, this is the step input. This is your second order system, which is defined by this transfer function. So the output looked like this one. This is for overdamped, overdamped. This one for critically damped, and these ones for underdamped system. Zeta is equal to zero point 0.2, zeta is equal to zero point 0.5, zeta is equal to zero point 0.7, and these are the overdamped. So all values of zeta are here, and the equation or the response we obtained it in this form: sine term plus cosine term, or we defined it only in terms of sine, omega dt plus the angle phi we defined earlier. And we said this one will be the transient response for the when the system is subject to, this is the angle phi, when the system is subject to a step input, we obtained this equation or this response. So from here, we can calculate the response specifications. So the delay time, what is the delay time? The delay time is the time for the response needed to reach half of its final value the very first time, which is given by this formula. TD will be 1 plus zero point 0.7 zeta over omega n. So here, from here to here, this is the delay time. If the total time to reach مثلا this one is the total time to reach the 100%, because this one will be the 100% line or the steady state line. This is the steady state line. Steady state line. So we assume that we have a response that is due to unit step input minus to unity, and this response will go to the steady state value, and this one is the steady state line. So the time for this one, the time from here to here is, let's say this is the time needed for the steady state line. So we need half of this time. Half of this time is 50%, which is this one, TD. It's called delay time to reach 50% of its final value. So if it is in the steady state line is one, is one. So 50%, at 50% it will be here. So if you look at this time from here to here, you will see that this time is reached from here to here. I will redraw this. So the response will reach the time for the response to make 100% value. The steady state line 100% is this line, steady state line. So the response when it comes to this is the response for total steady state line. The response reached 50% at this time. 50% is from here to here. Only from this line or from this line, it's the same thing, 50% and 50%. If you look here, the corresponding time here from here to here, it's called the delay time. The delay time, so it's calculated by this formula. 1 plus zero point 0.7 zeta over omega n, and this is experimental values. This is experimental value. So we know the delay time now is the time for response to reach half of its final value. The rise time. The rise time is, we have many definitions for this rise time. The textbook defined it from the time needed for the response to reach from 0 to 100%. So the textbook defined it like this. This is the TR. It's known as the TR from here to here, from 0 to 100%. This is called the rise time, TR. Many textbooks give the time to be either from 10%, from 0.1 to 90% or 0.9. They can take this as the rise time as it is shown here. This is showing also the rise time here. Some textbooks take from 5% to 95%, or from 0% to 100% of its final value. For the second order system under damped, we use the standard value is from 0 to 100% rise time, and the formula for it, the formula is simply this one. You calculate it from the formula. TR will be 1 pi minus beta over omega d. And this beta needs to be calculated, but in radians. In radians. Beta should be in radians. So pi is in radians, beta should be in radians, and omega d in radians per second. So if you say radian, at the end of the day, we'll have radian. The numerator will be radian divided by radian per second. You simplify radian to the radian, and you will find 1 over second will give you second, which is a time, rise time. Now, how to find beta? Beta should be find this way. This is how to find beta. Here, Beta is given by this. We have the poles located in the S-plane. This is the pole. It has a real value, zeta omega n, and omega d or omega n1 minus zeta square. So beta will be the angle made by the pole at this position. So either it will be cosine minus 1 zeta, or it will be sine minus 1, 1 minus zeta square, or 10 minus 1, 1 minus zeta square over zeta. These are all the values of beta, how we can find them. So the rise time at this position, if we take it at 1, we said the rise time will be from here. So at this value here, for the rise time, at this value, you see that the response is equal to 1. That's why we are putting 1 equal here, 1. So the response, Ct, at this value is equal to 1. And this is our rise time from here to here. This is Tr. Now Tr can be calculated from this formula. Just equate this. Ctr is equal to 1. Since we know that 1 will go with 1, and we know that exponential minus zeta omega n is not 0, so to this term that is inside is equal to 0. This term is equal to 0, or this term is equal to 0. This will give you 10 omega d Tr is equal to minus 1 minus zeta square under the square root over zeta. If you solve for Tr, you will find Tr will be 1 over omega d, 10 minus 1, this angle that I am calling pi minus beta over omega d. So pi minus beta will give you omega d here. واضح شباب? So this is the angle beta that is defined here. Beta is this angle. So beta is defined in equation 1025. We clearly, to obtain a large value of Tr, we must have a large value of beta. Any question? So this is the rise time, how to find it. The formula is ready. The angles is ready here. It's just the angle made by the poles. And beta needs to be expressed in radian because the time is expressed in radian per second. We also define the peak time. Yani what is the time for the response to reach the peak? The time made from here, from 0 to the peak time. The peak time is defined to be the time required for the response to reach the first peak of the overshoot. The first peak, not this one or this one. So it is given by this formula. Tp will be pi over omega d, or pi over omega n, 1 minus zeta squared. Now this peak time, Shabab, how we can get it? We know we have the expression for the response. We have C of t. The expression of C of t is given 1 minus exponential minus zeta omega nt, and then square root of kada sine kada. This is a maximum point here. We can obtain this value. We can obtain this value just by taking the derivative d over dt of ct. If you differentiate this dct, the response, if you differentiate it with respect to time and equate it to 0, you will find the value for the peak time. And this is what we are doing here now. We are taking the derivative of ct of the response with respect to time. When we differentiate it with respect to time, we get this expression. Since this one is not 0, this one is not 0, so meaning this term will be 0. Sine omega dt equal to 0 should give you omega dt equal to 0. متى يكون omega sine is equal to 0? Sine always is equal to 0 here at this value pi, and then another pi 2 pi, and then another pi 3 pi, and so on. So it is going this way. So 0 pi 2 pi 3 pi n pi. So the first value for the first over p, the peak, will be when n is equal to 1. The first peak will be when n is equal to 1, or Tp will be equal to pi over omega d. We know omega d is equal to omega n 1 minus zeta squared. This is known as the peak time. So I'm talking about the peak time here. This time from here to here, this is the derivative is equal to zero here. This is the peak time, how we can get it from here. This is called the peak time, the response to get the first peak. The first peak we are putting Shabab n is equal to 1. Then we have n pi. This is true sine omega dt is equal to 0 if omega d is equal to n pi. When n is equal to 1, this is the first peak. And we found it this way. Tp will be pi over omega d. Tp will be pi over omega d. Or correspond to one half cycle. One half cycle معناته قبل ما cycle will turn. This is, and from here to here is one cycle. The first peak will correspond to the first half cycle. This is known as the peak time, the time for the response to reach the peak. The maximum percent overshoot, which means how much my system will overshoot, will go beyond the line of 100, the line of 100, called the maximum percent overshoot. And it is defined like this. The maximum percent overshoot MP is the maximum peak value for the response of the curve, which is C of t versus C infinity. So because لأنه هنا it goes to infinity, so we'll take it C of infinity as equal to 1. And we defined it like this. Maximum percent overshoot will be C at time t is equal to P. What will be the value here? Minus the value of infinity here over the value of infinity. This is called the maximum percent overshoot. It has a value for that, or a formula for that, which is this one. The maximum percent overshoot will be the value of at time minus the value of infinity. So this will be exactly this value, minus exponential minus zeta omega t. We know that the maximum at Tp is pi over omega d. So we substitute time here by pi over omega d. It will be cosine sine pi 0 plus cosine pi minus 1. So at the end, if you solve this equation, this is 0, this is minus 1, minus multiplied by minus will give you plus. So you end up by having this value. MP, maximum percent overshoot, can be obtained when we get this formula. Minus pi zeta over 1 minus zeta squared. Or you can get it from the formula. Sorry, you don't have the textbook, because in the textbook they are giving you also this curve. Here we have the damping ratio in the x-axis. In the y-axis we have the maximum percent overshoot. And you see, as the damping increases this way, the maximum percent overshoot decreases. So this is also, you can use this chart for the maximum percent overshoot. So this is the maximum percent overshoot. With increasing the damping, the maximum percent overshoot decreases. So there is a value here. I give you an example. Okay, you can find it also, zeta, since we have the maximum percent overshoot given by this, MP is equal to this. If you take the log of both sides, you will be able to determine zeta just when we know the maximum percent overshoot. What will be zeta if you have مثلا 60% overshoot? At 60% overshoot, this is what we have here. This is 60% overshoot. You draw a vertical line. It crosses here the damping ratio. It is about 16% or 0.16. 0.16 is 16%. At 30% overshoot, here, we have about let's say 38%, and so on. At 10% overshoot, at 10% maximum overshoot, we have 60 or zero point 0.6 damping ratio, and so on. So you can use, if you are given the damping ratio, you will be able to calculate the maximum percent overshoot. If you have the maximum percent overshoot, you will be using this one to calculate the value of zeta. To calculate the value of zeta is just use this formula. So this formula will be ln of mp over square root of ln mp square plus pi square, which looks like the formula we defined it for, if you remember, for the logarithmic decrement. Here, for example, here we have the steady state value. The steady state value is 0.75. This is the final value. So, and the maximum value here, is about 0.97. 0.97. So the maximum percent overshoot, yani percent about this one as a percent, it goes 0.97 minus 0.75 over 0.75, which is 29.3%. So the maximum percent overshoot in a MP will be 29.33% from here to here. And you compare this one, this amount, as a percent with this, it is 29.33%. Any question, Shabab? Any question? Any question?
It is clear, Doctor.
Okay, Shabab. Okay. The settling time. What will be the settling time? The settling time, in fact, it is the time for the response to reach the steady state value. Here also we have some definition or some criteria. The settling time, Shabab, will be decided by this value here. You know, when we draw this value response, we said it is controlled by this. By this curve, I am putting with this. We are writing exponential minus zeta omega nt. So the response to go to the final value, to the steady state, it will be controlled by this amount, by this envelope. So if the error, usually the 2% error, يعني between this and this, the error will be 2%. 2%. If this error is 2% and this one will be controlling, so we will just write here, this is the guy who controls this. We will write exponential minus zeta omega nt will be equal to 0.02. This is based on 2% criteria. We call it 2% criteria. If we solve this equation, it will give us minus zeta omega n t will be equal ln of 0, 0 t. So we will solve for this time. If we solve for this time, we will find this one will be something like ln of 0, 0, 2. Ln of 0, 0, 2 will be how much? If you have your calculator with you, it will give you, let me just calculate it, ln of 0, 0, 2. It is 3.9, which is 3.9 and 4. So TS settling time will be تقريبا 4 over zeta omega n. Zeta omega n. So TS, if we solve this one for TS, the settling time based on 2% criteria, 2% error, the settling time will be 4 over zeta omega n. The settling time here, we calculate it from here to here, Shabab. يعني it will be something like, let's say, up to here. This is the settling time. So the time for the response to settle and stay within 2% error. The settling time is the time for the response to settle and stay within 2% of the final value. There are many definitions. These are many definitions, but the based on 2% criteria is this one. So this is here, the settling time is somewhere between here and here. Now, if I take the time, Shabab, based on 5% error. 5% error معناته the error will be larger. يعني the error will be larger than the 2%. The error will be like here, from here to here. And the error for this time, or the time for this error, will be less in this case, less for 5% error. 5% criterion will give you a time that is exponential minus zeta omega n equal 0.005. If you compare this time here, you will find that this time is 3 over zeta omega n. 3 over zeta omega n is less, أقل من 4 zeta omega n, لأنه it will be somewhere هنا. بينما settling time for the other one is here, from here to here. Is this clear, شباب? So 4 over zeta omega n 2% criterion, 3 over zeta omega n 5% criterion. You can take any criterion, 3%, 4%, it doesn't matter. Just take this exponential minus zeta omega n will be equal to the error هنا. How much error you want, this is what you get. Because this one will be controlled by the envelope, the exponential envelope. Is there any question شباب هنا؟ تفضل هاني.
دكتور هنا يعني معناته انه اذا كانت تايم مور ليس يعني مثلا خلينا نقول 2% ومور ليس يعني السيستم مور ستيبل ولا كيف؟
No,
what is the benefit يعني
yeah,
طيب
if we want, depending on your application, some people they don't care if it is 5% criteria, if the error is 3 over zeta omega n. No, but some people would like their system to be and stay within 2% criteria. As you see the error هنا how much. يعني you reduce the error as much as you can. Of course, if you reduce the error, it means it has a price. The price you send is you will stay a long time to achieve that. The settling time will take more time to achieve that. بينما if you don't care about the error, is not important for you, it will take, you will pay less. The time will be shorter, as simple as that.
Okay, thank you.
Okay. So the time constant always is, we defined it for the response to stay within 63% of its final value. You remember this value. Here, the time constant will be at minus zeta omega n, which is given by tau is equal to 1 over zeta omega n, the second order system. So the time constant will be 1 over zeta omega n for the second order system. هنا so شباب, all these values are determined now. If we know the TS, this is the TS time. TS, if you remember, we define it as the settling time to stay within 2% of its final value. This is the peak time, TP. The time from here to here is TP. This is the settling time is here. This is the rise time is here from 0 to 100%. The rise time. This is the delay time for the response to reach 50% of its final value. And if we know this maximum percent overshoot, if you have only these times, you will be able to draw your response. You join this point with this point, with this point, with this point, with this point, and you have an idea about your response, transient response specifications. So if these are known, you will be able to know your response. Now, when we want our system to be, always we concentrate for the system to be fast. We want our system to be fast. If it is fast, means we want a fast settling time and fast rise time. Fast TR and fast TS. Does not excessively overshoot the desired value. We don't want our system to make overshoot, otherwise maybe your system will break. So you have to have a reasonable design. The design will specify how much overshoot you need to reach and remain close to desired reference value, which means we want the steady state error to be as small as possible. These are some design criteria when we design the specific values. Some effects of the poles هنا شباب, if you for example keep your poles, the imaginary pole is constant here. What does this mean? If we keep this one is constant, the imaginary pole is constant, and we are moving here. We are moving here. This means what? We are changing the values here. Here it means that I am changing sorry, I'm keeping zeta omega n constant, as you can see. Then along this line, either this line or this line. Let's take this line first that I am putting circles. This line. If we have our poles are constant along this line, are constant along this line means and no that our response is having the envelope is constant. The envelope is not changing. The envelope is constant. It will not change. Then zeta omega n is always constant. From here to here is constant. So what will happen to the response? The response will stay within this limit. It will not move. It will do this. It will maybe do this, but it will stay within this limit. It will go to the steady state value within this limit, does not go beyond the envelope. So this is what it means. When we keep this one, zeta omega n is constant. واضح شباب? Is this clear? Is this clear? One student يعني can ask this legitimate question. He can tell me why you are telling us if zeta is changing and omega n is changing. Fine, ما في مشكلة. Zeta is changing, omega n is changing, but their product is constant. Their product is constant. يعني حاصل ضرب تاعهم is equal to constant. نعطيك مثال. 4 times 3 is equal to 12. 6 times 2 is equal to 12. 1.5 times 6 is multiplied by 6 is equal to 12. Always the product is constant. Even the variable is changing. Now we are looking just for the real value, which is constant. If we make this one constant, means I am making the envelope constant. The envelope is not changing. Any questions, Shabab? So let me go to the other side. Now, تفضل يا هاني.
بس دكتور الانفلوب متحكم بالتايم، يعني time as the time increasing it will decrease.
No, zeta omega n, zeta omega n. Zeta omega n. Zeta omega n. The time is zeta omega n is like this, is fixed. Zeta omega n will be always like this. It will not change to this one. Time is here. Time is changing along this one. But what I am saying, you will not have this case. You will not have this envelope. You will not have this envelope. You will not have this envelope. The envelope, the control of zeta omega n is controlling these values here.
Okay, I see. Yeah, clear.
هنا zeta omega n is equal to 1. هنا zeta omega n is equal to 2. هنا zeta omega n is equal to 3.
Yeah,
so
clear.
Controlling this. واضح؟
Yes.
Is this question واضحة شباب اللي طرحها هاني؟ So let's go on this case now. شباب هنا. Let's go to this case. When we have this value constant. This value constant, what does it mean? معناته I am keeping omega d constant. I'm keeping omega d constant. Omega d constant means I'm keeping, if you remember, we said in this type of plots, we said we have two plots, the envelope and the sinusoid that is inside. Now, once I keep this one constant, means I am keeping the overshoot constant. The overshoot and the behavior will be constant. Now, if I bring this one here, I can change the envelope now, okay, but the envelope will be, or it will be always constant. It will be behaving in the same behavior like this. So if you look here to the line of zeta, zeta will be constant, or the damping, the amount of damping will be always constant. That's why and keep the sinusoid will behave in the same behavior. These are the two important things. We can have the poles varying along these lines. Poles varying along these lines means having constant zeta. Zeta is not changing. You'll have always the same damping. So these are the three values we want you to know. Now, small, quick example to just explain the idea. Consider the system shown here in this figure, where zeta is equal to zero point 0.6, omega n is equal to 5. Let us obtain the rise time, TR, peak time, TP, maximum percent overshoot, and settling time when the system is subject to a step input. So from here, if you see, Shabab, the final value or the values for zeta and omega n are obtained, zeta is given. So zeta omega n, we can get it. Zeta omega n is equal to 3 هنا. And omega d is equal to 4. Then we have zeta is equal to 0.6 and omega n is equal to 5. So this is 6 or 0.6 times 5 will give you 3. This is for zeta omega n, which is the real part of the pole. And this one, omega d will be omega n 1 minus zeta square. Omega n is given to be 5. Zeta is 0.6. This one will be, if you want, the imaginary part or omega d. So we have omega d and we have the real part. So the rise time, if you remember, the rise time we defined it to be pi minus beta over omega d, where beta was defined to be 10 minus 1 omega d over zeta. Omega d is 4. We calculated it here. Omega d is 4. Sigma, which is the real part, is 3. We calculated. So it will be 0.93. So beta will be 0.93. And TR, the rise time in this, will be 3.14 minus 0.93 over 4. This one is beta here. This will give you 0.55. So the rise time will be 0.55. The rise time will be a smaller time. It's not like the peak time. It will be smaller than the peak time, and it will be smaller also than the settling time. The peak time, Shabab, if you remember, will be pi over omega d, or 0.775. You remember TR, we calculated it to be 0.55 seconds. This one is the peak time, pi over omega d. The maximum percent overshoot is exponential minus pi zeta over 1 minus zeta square, or sigma over omega d, the real part over the imaginary part, times pi. This will give you 0.0095. So the maximum percent overshoot here is 9.5%. So this is 9.5%. واضح شباب? Or you can go back to your sheets or the formula. If you remember, I gave you here. This one was the maximum percent overshoot, and this one was zeta. See, how much you calculate the maximum percent overshoot. Here we have damping of 0.6. Damping of 0.6. If we go back to the slides before we gave you for the maximum percent overshoot, 0.6 will give you here, Shabab. If you go and take the 0.6 here of damping ratio, 0.6 damping ratio will give you a value that is somewhere here, almost 9.6, قريبا 10%. So this is the maximum percent. We found it from the formula. Using the formula, we found 95% or 9.5%. For the 2% criteria, settling time will be TS, will be 4 over zeta, or 4 over zeta omega n. This is zeta omega n, which is 3, which is 0.33 seconds. For 5% criterion is 1 second. See the difference, Shabab? See the difference? See the peak time, TP, and see the rise time, TS. The rise time, TR, was 0.55 seconds. So here, your settling time is the largest time. Usually the settling time is the largest time. If you go back to your response, something like this, here we have, let's say this is our settling time. TS is the largest time, TS. TP is this one. This is TP. And the time for this one is TR, or the rise time. We are calling it peak time, and then the rise time is this one, from here to here, rise time. The delay time, we did not calculate it here. It's from here to here. From here to here. This is known as the delay time, TD. So this is how do we calculate these time specifications. MATLAB, if we go to MATLAB implementation, usually we do MATLAB implementation. You define your transfer function. Your transfer function or your differential equation has this transfer function. You just give the numerator, and then you give the denominator 1 to 5. You just type step sys. Step sys will give you this response, and then step info will give you the rise time, will give you the settling time, will give you the overshoot, and will give you the peak time. So these are the how we can calculate. So if you go from here to here and you compare approximately, you compare the with the formula we calculated, you will get these values here. Another example here, Shabab, for the system shown in figure 513, which is here, determine the value of K. Here, this is a design value because you are defining the value of K, and the velocity feedback constant KH, this is a feedback here, so that the maximum percent overshoot to unit step response is 0.2. So MP here will be 20%. Maximum percent overshoot will be 20% or 0.2. And the peak time is 1 second. We want also to have peak time to be 1 second. TP will be 1 second. This is a design problem. So with these values of K and KH, obtain the rise time, TR, and settling time. Assume that J is equal to 1 kilogram meter square and B is equal to 1 Newton meter per radian per second. First of all, Shabab, we need to find the closed loop transfer function, the overall transfer function. Yesterday, we have seen how to reduce the block. So we have this block and this block are in feedback. If they are in feedback, you just calculate this one. This will be simply K over GS plus B times KH. So if we calculate this one, this is here, this block will be this block. Now we have this block combined with this block in series. Combined in this block in series. So all we have to do is multiply this by S. You know, this is 1 over S, multiply by this. So this is what we get. We got this one, K over S, JS plus B, KH. Now, we need to define this feedback also to obtain just one block relating the output C of S to the input R of S. So the formula will give you C of S over R. Remember here, this is J of S, and this is H of S. You remember yesterday we obtained C of S over G of S is equal to J of S over 1 plus J of S times H of S. If we apply this formula, we get here K over J over S squared plus B plus KH over J times S plus K over G. We are trying now to write it in standard form. We write it in standard form, second order equation. So we have K over J will be omega squared, and we have B plus K times KH over J will be twice zeta omega n. So to compare it with the standard second order equation. So we have omega squared n will be equal to this, K over J. K is given, okay, we are looking for it, it's not given in fact, but J is given. We have twice zeta omega n, which is not given, but we can get it from the maximum percent overshoot. Then maximum percent overshoot is zero point 0.2, and we have the value of B. So let's continue now and see how we can get this one. The maximum percent overshoot, since it is given to be zero point 0.2, given this is given, you can calculate zeta. What will be the value of zeta? So solving this equation from here to here, solving this equation, you will get this one will be 0.456. Once we know 0.456, we know, Shabab, the peak time is given to be 1 second. Since the peak time is given to be 1 second, the peak time is pi over omega d, and omega d itself is given to you, and it is equal to pi. It was given to us to be pi. So because this one will be simply pi, so if you equate this and this, you solve for omega d, you will find it to be pi. Omega d is equal to pi. We know the relationship relating omega d to omega n 1 minus zeta squared. Zeta, we found it 0.456. Omega d is known to be pi. We will be able to solve for omega n. Omega n will be 353 radian per second. So once we solve for omega n, we know zeta, we know the other parameters. So k, from the last transfer function, we found k is equal to j omega square n, and this will give you 12.5, لأنه omega n is known. Omega n square is known, it is 12.5 square. So then we have to solve also for twice zeta omega n from the equation we found. So we found kh to be 0.178 square. Now, once we found k, and once we found kh, we are done. So we are done here. Back and calculate the rise time. The rise time will be simply pi minus beta over omega d. Pi over minus pi omega d is given, if you remember, we found it. So it will be simply 10 minus 1 omega d over zeta, sigma. We know, since we know zeta and we know omega n, this will be sigma, which is here. And omega d will be simply omega n 1 minus zeta square. We know all of this. So this one will be 10 minus 1, 195 or 1.1. So the rise time will be 0.65 seconds.